Hi, I'm Zor. Welcome to New Zor Education. This lecture is a continuation of the topics called Combinatorics, and it's about permutation of the set of objects. Some of them might be identical. Now, this lecture is part of the whole course, which can be found on unizor.com. Together with notes for this lecture and some exercises, etc. So I do recommend you to go to unizor.com to work with this educational material. Okay, permutation with identical objects. Well, first of all, let me just very briefly recall what is a permutation of the set of different objects. Well, as you remember, if you have certain number n of different objects and we would like to put them in certain order, well, question is how many different orderings exist. Well, for the first place, we have n different choices. We can take object number 1 any one of the given n objects. But for the object number 2, we have only n minus 1 objects remaining because 1 is already taken. So I have to multiply it by n minus 1 if I would like to find out how many different pairs, number 1 and number 2. And then number 3 comes along, and this is this, etc., up to the remaining only one object for object number n. So the whole thing actually is n factorial. Different orderings of different objects. But what if some of our objects are the same? Well, here is an example. For instance, you have a set of objects, let's say 3 letters, A, and B. So 2 letters are identical. Now, question is how many different permutations exist of this particular set? And I'm talking about permutations of 3 different letters. Well, letter B can be on the first place, and then there is no other choice but putting A and A. Letter B can be on the second place, and this is the combination. There are no others with B's in the second place. And finally, B can be on the third place as object number 3, and that would be the combination number 3. There are no other combinations. Now, if our objects were different, 3 different objects, I would have 3 factorial, which is 3 times 2 times 1, which is 6 different combinations, different orderings. But if some of the objects are the same, I have significantly smaller number of different combinations. Now, why? Let's just think about it. Well, the answer is quite simple, and to illustrate it, let me just do it with a slight twist. Now, I will still have A, and B, but I will put indices here, A1 and A2. A1 and A2 are indistinguishable from each other. I just put these indices to distinguish them on the board to explain what I exactly mean. Now, each combination can be either A1, A2 or A2, A1. Now, they are indistinguishable, and that's why I initially put only one combination, BAA. But if these are all different, that would be different combinations. So these 2 combinations are actually glued together into one when we are changing places among the identical objects, because they are indistinguishable. So these 2 combinations are exactly the same from the visual perspective. This is letter A, and this is A and A. It's just 2 different letters A, but we do not know this since we do not really have any distinguished characteristics between A1 and A2. Now, same thing here. It can be A1, A2, or it can be A2, A1. And same here. Now I have 6 combinations, exactly what I really needed. But again, out of these 6 combinations, these pairs are constituting exactly the same permutations of initial characters, because this is BAA and this is BAA. So my point is that if you take all the combinations where identical objects are on the same places, in this case it's this pair of combinations, or this pair of combinations, or this pair of combinations. So within each pair, my identical objects are exactly on the same places where they are. This is number 2, number 3, and this is number 2, number 3. This is number 1 and number 3, this is number 1 and number 3. And this is 1 and 2, and this is 1 and 2, the places. So if you will take as a group, so this is a group of combinations, and this is a group of combinations. So each group is actually a one permutation. So even if you have 6 different permutations, if you are if you put indexes for identical objects, in reality, since we can group them together where like objects, identical objects, are exactly on the same places, and all these elements within the group are indistinguishable from each other, they constitute one particular permutation. Now, the question is, how many elements are in the group? Well, let's just think about it. This group contains all the different permutations where A and A are standing on places number 2 and 3. And I can change within this group my identical objects any way I would like, and I will get only elements from this group. Now, if I had, for instance, more elements, I would have more identical elements. I would have more elements within the same group. But in any case, the number of elements within the group is equal to the number of permutations of only like objects, only identical objects. Because if I have, let's say, one particular combination, then I'm changing the order of these identical objects. I still have exactly the element of the same group, right? So no matter how I change the order of identical objects within the places where they are, my permutation is actually the same because these elements are indistinguishable. So what I would like to say is that each group contains exactly as many elements as number of permutations within the identical object. So if my identical objects are numbered 2 and the number of permutations is 2, it's A1, A2, or A2, A1, right? 2 factorial is 2. So what I mean is that if my number of permutations only within the only within the identical objects is certain number, like in this case it's 2, I have to divide the total number of theoretically possible permutations. If all objects are different, I have to divide it by the number of permutations within the identical group. Because every permutation within the identical group produces the element within the same group of indistinguishable permutations. So that's the very important topic. Now, let me just make one step into a little bit more complicated area. In this example, we had only one group of characters, A and A, which is identical. Now, what if we have 2 different groups? Well, example, for instance, is A, B, 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 and C. And let's say I'm talking about the permutations of this group of, how many? 6 characters. Same thing. If I will index them so they look differently, but in reality A1 and A2 are indistinguishable and B1, B2, and B3 are indistinguishable. what I can say is that out of 6 factorial of different permutations, I have to divide this by number of permutations of the group of 2 and number of permutations group of 3. Why? Because if you will take, let's take any one particular permutation, A1, A2, B1, B2, B3, and C. And now I will repeat it, but change the order of this. Let's say B2, B1, B3, C. These are indistinguishable, so these are the same permutations. So how many times I can just write down all these permutations which are really indistinguishable? Well, 3 factorial times, right? And then with each of these I can change the order of these, and how many of these different orders are 2 factorial, right? So in this case I have to divide 6 factorial by 2 factorial and 3 factorial, because I can change the order within this group and change the order within that group, and all of these are constituting exactly the same permutation of the entire set of 6 characters. Now let's go into a little bit more complicated case. Let's go back to only one group of identical characters, but in this case we will consider there are many of them. So I'll use the indices. So x1 and x2, etc., and xn are exactly the same object. These are indistinguishable. I'm just using index to show the point which I would like. And then you have different characters, A, B, C, whatever. So if you have this particular case, so all x's are indistinguishable, and then all different characters you have. And let's say again you have number n of all characters. Now obviously if I consider them different, I would say n factorial, right? This is the number of permutations if all characters are different. But now let's think about, if I have one particular permutation, let's say this one, then down below I can put different permutation within this group only. I can put x2, x1, for instance, xn, a, b, c, and it will be exactly the same permutation of the entire set. And then I can change again the order and again. And how many times I can change the order? Well, n factorial, small n factorial, right? Because this is the number of different permutations of this particular set of identical characters. So any permutation which is different only within this group of first n objects is only one permutation of the entire real indistinguishable permutation of the entire set. Right? So if I would like to know how many real permutations of the entire set, I have to divide n factorial to n small factorial. Alright. Now let's switch to two groups. Let's say you have n1 of x's, and then n2 of y's, and then abc. What happens here? Same thing. We already covered this, but in the case of like 2 and 3. If you have n1 identical objects of one kind and 2 identical objects of another kind, and then all other objects are different, then n factorial should be divided by number of permutations of the first group and number of permutations of the second group. Why? Because again, exactly the same thing. If you write any permutation of the entire group, if you consider these characters different, and then you start changing only within this group, you will still have exactly the same real permutation of the entire thing, because these objects are indistinguishable. So all these which are different only within the order of x's should be considered as one permutation. And now you can also change the order of y's. And that would also be exactly the same permutation. And each of these goes with each of that. That's why we're multiplying them. So I basically came to general formula for the following case. If you have n objects and out of them you have n1 objects of one kind, one type, and then n2 of another type, identical within itself, and then n3, etc., nk, then the total number of permutations of this group is n factorial divided by these, by the product of these factorials. Because again, as soon as you write any particular permutation of the entire group, you can change the order within the first group anytime you want, and there are n1 factorial different things, and you still get exactly the same permutation of the entire set. And for each of these, you can actually multiply it. You can change the order of the second group only within the group. And again, there are so many different n2 factorial different permutations within the second group of identical characters. So basically, that's what that's the formula which you will come up with. I have explained this formula. I didn't really prove it. It can be proven by induction, let's say by the number of group K, something like this. And then another interesting thing. What if I will consider all these different elements as groups of identical elements, but the n would be n keta or whatever, and third in this case is equal to 1. So it's a group of one element, right? Would the formula be still valid? Well, obviously, because if it's a group of one element, one factorial is still 1, so it doesn't really matter whether you put these ones or not. So if you have single different objects within the set, you can still consider them as elements of the groups, but the groups contain only one element, and the formula is still valid. So you can say that if you can divide your total number of objects into certain groups, and within group you have n1 element of one kind, and two elements of another kind, and nk elements of the case kind, and within the group all elements are identical, then this formula actually represents the number of permutation of this group. Well, let's check out whether this particular formula is valid for our first case. You remember we had A, and B, right? A, and B. And we had only 3 real permutations. Now, in this case, I have only one repeating group of repeating elements, and the n1 is equal to 2 in this case. This is the number of elements in the first group. And the second group, I can specify the second group as having only one element, right? Now, what our formula gives us, 3 factorial divided by 2 factorial and 1 factorial, which is 6 divided by 2, which is 3, which is exactly what we got. So this is the correct formula. Now, another particular example. Let's go into some extreme case. Let's say all elements are the same. So what do we have in this particular case? So this is the case of like this. Well, if all elements are the same, then no matter how we will change their order, it's one permutation, right? So we should have the answer 1. Number of permutation is equal to 1 if all elements are identical. Now, in this particular case, what do we have? We have n is equal to whatever it's equal to. Now, n1 would be equal to n, right? This is the size of the group, and they're all identical, right? So the size is the entire set. And there are no n2, n3, nk, etc. So this is all out, and n1 is equal to n. So you have n factorial divided by n factorial, and you have 1. So the formula again holds. And another extreme case when all elements are different. So we have n groups. So in this case, k is equal to n. This is number of groups. And each group, n eta, has only one element, because all elements are different, right? So each group contains only one element. So in this particular case, what do we have here? Well, we have n factorial divided by 1 factorial, 1 factorial, 1 factorial. These are all ones, so we have n factorial, and this is the original formula for the number of permutations. So, what's the most important lesson which you can get from this particular lecture? If you have certain number of elements identical in the set, and you're looking for permutations, obviously, if you will permute only the elements within that set, then the permutation of the entire set remains looking exactly the same. So if you change the order A and A, the permutation would be exactly the same. So that's why we are dividing the total number of permutation, which is n factorial, into the number of permutations within that one group. And if you have more than one group, you have to divide it by another factorial, another number of permutations within that second group, well, depending on how many elements are there, etc. So that's the most important lesson. You have to divide by permutations within each repeating group. Okay, that's it. That's all I wanted to talk about today. It might be slightly more difficult than the previous lectures about permutations, but I hope I explained it well, and there are different problems which will obviously use this particular property of repeated objects, of identical objects and their permutations. Always go to unizor.com if you would like to engage in the whole educational process, because it contains the course, and registered students can take exams, etc. So I do encourage you to go to the website rather than just watching this particular lecture on YouTube. That's it. Thank you very much, and good luck.